And now it is time for part two. It is time to teach you the easiest way to solve systems of equations. Now, I'm contrasting easy with simple here, right? Because solving by matrix inversion is very simple. You invert the matrix, you multiply, you're done. This can't get much simpler than that. But remember, inverting matrices is painful for large matrices. So we want a method that is computationally more tractable. And how do we do that? We do that with Gaussian elimination. So this is named for the same Gauss that everything is named after, Carl Friedrich Gauss, born in 1777. You know, the US was trying to figure out whether to exist or not. And meanwhile, like one of the greatest mathematicians ever was born. Now, he's known for so many things that there's literally a list on Wikipedia, like a whole page that is list of things named for Carl Friedrich Gauss. The dude was an absolute genius. So as much as he gets credit for so many things, he actually doesn't deserve credit for this one. Carl Friedrich Gauss did not invent Gaussian elimination. It turns out it was named for him in the 20th century by people who didn't know history. He didn't invent it. He did develop the notation, more or less, that we use today. And that notation is slick and it certainly reduces the pain in the process. So, like, he gets some credit, but he did not invent the method. He really didn't invent the method. The method was invented at least 1800 years before he did it. And it makes sense because algebra is really old. People have been doing algebra for literally thousands of years. Solve for x, right? I have an unknown quantity of something, but I know how it relates to things that I do know. So this is from the, please forgive me, I don't speak Chinese, but it's the Zhouzhang Suanshu or something close to that. And that's the modern pronunciation. It would not have been pronounced that way in the year 179. But it's the 9 chapters on arithmetical methods or something kind of close to that. And look at this problem. Suppose we have 3 bundles of top quality cereal, 2 bundles of medium quality cereal, and 1 bundle of low quality cereal with blah blah weight 39 dough. Like, it's an algebra problem, right? People have been doing this for so long. And this method, Gaussian elimination, looks like it was invented in China around 2000 years ago, give or take. So that said, now in the West, it's called Gaussian elimination, and here we are. All right. A couple of you were like, hey, tell us more history. So there you go. There's more history. Let's talk about how to do this thing. Again, we are looking at equations that fundamentally are matrix equations. It is a whole bunch of coefficients multiplied by our variables in different combinations. And those linear combinations of variables add up to some constant. If the constant is 0, we call them homogeneous. If the constants are not 0, we call them inhomogeneous. And we saw last time that there's these conditions that you can ask about the inverse of the matrix of coefficients to learn stuff about the system of the equations. But we're not going to be inverting matrices today. Not really. I do want to say something I didn't say last time, because last time we only dealt with inhomogeneous systems. And that's because they're actually easier. Even though less stuff is 0, it's easier to solve because you are more likely to get unique solutions. With homogeneous systems, you have this property on the screen that if you have 2 solutions, any linear combination of those is also a solution. And this is where the matrix and vector notation is so powerful in understanding what's going on. Because if you have 3 variables like x, y, and z here, you think of that as a vector of variables, like you're finding a direction in space that solves that equation. And so it makes sense that any other thing, any other vector that's pointed in the same direction would also satisfy those geometric constraints that are encoded in these equations. So linear combinations of solutions for homogeneous systems are also solutions. And people saw this when we were doing the linear independence thing. It can be tough to figure out how to solve those problems because you end up with infinitely many solutions and you end up with a lot of like, I guess I just choose a value for my variable now, it's because homogeneous consistent systems are not, um, uniquely constrained to a single value. They give you families of solutions. And that means that for those classes of problems, matrix inversion is not going to be a great strategy. What we're going to do instead is to do, here we are, Gaussian elimination. So it takes a little bit of thinking, but it works for a broader class of problems than matrix inversion does. And it is also computationally less intensive for very large systems. So I don't want to just be like, it's the superior approach. That's not necessarily true. Matrices with lots of zeros are very easy to invert, for example. And in science, we often deal with square matrices, and square matrices have nice properties that make them easier to work with. But, in a purely mathematical sense, at the end of the day, you can always use Gaussian elimination. It may not be the best tool for every problem, but you can be guaranteed that if the problem is solvable, it will work. Okay, I kind of mentioned this last time, but just a quick refresher because this is important, so it's worth repeating. Sometimes for algebraic systems, you get a unique solution. Sometimes you get no solution. That is going to be important here because when we're doing Gaussian elimination, sometimes you end up with a contradiction. You end up like a 0 equals 1 sort of equation, and you're like, oh, well, that's just not true. There's quite literally no solution to that equation, right? Tell me a value of 1 that equals 0. Or, yeah, okay, cool. But then, as I was just saying about homogeneous systems, there are cases where you do get infinitely many solutions. And while there will be relationships between the variables, you have free choices in just like picking, oh, I guess I'm going to make C equal to 3 now. And then that will determine the rest of the variables. But that free choice means that you have infinitely many options. Okay, let's actually do it now that I've said all that context. So the steps are, first, we're going to write this thing called an augmented matrix, and I'll show that visually very soon. But essentially what we do is we take our coefficient matrix and we just add another column to it. And that column will be the values of the constants on the right-hand side of the equation. So either the zeros, if it's homogeneous, or whatever those non-zero constants are, if it's inhomogeneous. You'll see that very soon. And then we're going to do what's called elementary row operations to simplify the problem. This is where a lot of the thinking comes in, but this is also what makes this method genius, is all you have to do is multiply and add. That's the whole thing. Nothing complicated. You multiply, you add, and you keep multiplying and adding until you have solved for one of your variables. And then at that point, you take that value and just like you used to do in high school, you plug it back into the equations and you learn everything else by plugging in those values. So augmented matrix, elementary row operations until the problem is simplified, get your last variable, substitute in that number to find the rest. That's how we do. What is an elementary row operation? I was like, it's adding and multiplying. Okay, but exactly what do you do? One elementary row operation is switching two rows in the matrix, just exchanging them with each other. This does not change the equations in any way, but it might make it easier to read. It might just make it like simpler to work with, easier to look at, and you have that option. You can write equations in a different order without changing what those equations are, and it might make things make more sense in your head. So that's our first elementary row operation. Next, you can multiply any row by a constant scalar. This is exactly analogous to what you learned in high school or maybe even middle school. I don't know, maybe you're smart about you can do anything you want to an equation as long as you do it to both sides of an equation. That's what we're doing here. We're saying take both sides of an equation, multiply them by the same factor. So that's our multiplication elementary row operation. And then finally, you can make essentially linear combinations of rows. So you can take one row, multiply it by something, and then add that to a different row. Remember, numbers can be negative as well as positive. And so this is how you take advantage of cancellation to simplify the problem, is by adding a multiple of one row to a different row such that stuff cancels out. And the reason that these are the three magic operations, switching, multiplication, and linear combination, is that they do not change the solution to the problem. They'll change the way the equations look, but they will not change the solutions of those equations. That's why these are the magic ones. Let's do an example, because that was very abstract. I'm going to write some equations. Da-da-da-dum. Here they are. It's three equations, three variables. We're back in algebra class. So first I write the augmented matrix. This is my matrix of coefficients plus one more column. And hopefully you can see here on the slide that that last column is just the values on the right-hand side of the equation. Those are my inhomogeneous terms in this case because it is an inhomogeneous equation. But if it were homogeneous, then these would just be 0, 0, 0 on the right instead. Okay. And then all of the elements in the left part of the matrix, those are the coefficients of the variables in my equations. So now we have this augmented matrix. It is time to start doing row operations. So I am going to add -2 times the first row to the second row. That's what I mean by R1, R2 is first row, second row. I don't know if that's a universal notation or if I just made it up one day, but there you go. We're doing a linear combination. So -2 times the first row added into the second row. Let's look at this real quick. So we'll have -2 times 1. That will be -2. So when I add it, this will cancel out. -2 times -2, that will give me a +4 here. And then -2 times 1, I'll be adding a -2 plus the -3 here. And so it'll be -5. And 0 on the right, you have to do it to the whole row because you have to do the same operation across the whole equation. Then we will be adding 0 times -2 to this 5. So it'll still be 5. All right. And that is great because it has now canceled out a term. Our goal is to turn things into zeros because zeros are easy to work with. So now we're going to add -4 times the first row to the third row. Because once again, it's like, ooh, look at that first term. 1 times -4 will be -4. And then when I add that to this 4, they will cancel out and I'll be making zeros. So after doing these two operations, I have made some progress. But we're not quite finished yet because our goal is to make the left part of the matrix fully triangular. And what triangular means is that the diagonal and everything above the diagonal can be whatever it is. But everything below the diagonal should be zeros entirely. That's what's meant by a triangular matrix, is numbers up top, zeros on the bottom, relative to the diagonal. So we'll need to do one more kind of row operation, or maybe more than one, in order to get this last number to be 0. Well, I'm going to flip row 2 and row 3. Again, this is an organizational thing. This helps me strategize. It just helps me think better. And why am I doing that? I'm like, ooh, there's a 1 sitting here. I love the number 1 because it's easy to multiply by. So I want to get that into my second row and then do some multiplication and addition acting on that 1. So I have flipped the rows. And then finally, I am going to once again make a linear combination, add -5 times row 2 to row 3. And sure enough, that'll be my 1 times -5. So when I add it to this 5, they'll cancel out and I'll be left with 0. And then after doing that, the matrix is fully triangular. Huzzah, right? I have my zeros down on the bottom and then my triangle up top is numbers. This is now fully reduced form. At this point, the hard work is done. We just have to get the values for the variables at this point. Because remember, these things represent equations. This is saying 10z equals 10. Well, that makes Z really easy to find. What a great problem. Someone smart must have picked this. Sorry. Um, and so then I'll know, ooh, Z equals 1 because 10Z equals 10. Now I plug that back into here. 1Y minus 3 equals negative 1. And so that tells me what Y is. And then I plug in above. And so we work our way from bottom to top. So Z equals 1, I said that. Then putting that Z equals 1 into the second equation, that lets us solve for Y. And so we have Y equals 2. And then I plug in Y equals Z into my first equation, and I will end up with X minus 4 plus 1 equals 0. And so X equals 3. And then we're done. Those are the solutions. So this is not like an entirely different universe from algebra that you've learned before. We're doing the organization of the work in a different way, and we are writing it in a really nice, clean format that is just easier to read, honestly. Finally, this method of getting the matrix triangular in form makes that final step of solving and substituting and getting numbers. It makes it really fast because, as I said, you just go from bottom to top and you're automatically doing one variable at a time and not having to like check what you've plugged into who else already and make some kind of strategic mistake. And now we write down the answer. X equals 3, Y equals 2, Z equals 1. Done. So that's how it works. Why does it matter? Always got to say why it matters. So, materials are made out of mixtures. I don't know if you've heard that before. Yeah, sure, there are pure substances. They're called elements, but whatever. Most things are mixtures. And when we're making mixtures, we have proportions of stuff. And so we have relative amounts of different quantities added together to make a total of thing. That's like the grain problem that I showed you at the start. It's the same stuff. It's all linear equations when you're calculating quantities to mix together. On a very separate kind of topic, though, oh my goodness, words. Finite element analysis, good job, is massive sets of linear equations. Because what we're doing is we're taking the system that we want to analyze, we're breaking it into a bunch of tiny little chunks, and on each of those tiny little chunks, there's a set of linear equations that relates it to its neighbors. Like if we're doing a mechanical analysis, you say, okay, I have some stress and strain in my chunk, and so I write my stress strain equations, and those are linear equations. And then you link those to the stress and strain in the neighboring elements, and you link those to the stress and strain in the neighboring elements. And so you end up with these huge, like potentially millions of element matrices that you are solving. When we're looking at chemical reactions, very often these sort of chemical balance and like reactant and output problems, these can be frequently reduced to linear combinations as well, where I have these quantities that react in a certain mole ratio in order to produce some kind of reactant. And so you have these coefficients corresponding to the different mole ratios and the different numbers of atoms of each element in your reaction that's happening. And so when we're doing synthesis in materials, like imagine you're making a polymer, you want to know how much of each constituent you use to add together in different proportions to make a total. But really, what if we wanted to do math for the sake of doing MSE? I said last time that I would tell you this time about how to invert matrices, and there's actually this crazy interaction between these two topics. So this is not required, but I do think it's very neat, and I want to share it with you before we call it a day. Now, when I wrote this down, I thought about correcting my typo, and I was like, no, this is actually really funny because I inverted the inverse of a matrix and wrote it as the matrix of an inverse. Oh, you guys, the struggle is real. Okay, so how do we invert matrices? We do it by Gaussian elimination. This is another way. And you're like, but I thought Gaussian elimination was for solving equations. Well, Gaussian elimination represents matrix actions, right? Flipping rows, multiplying coefficients, multiplying and adding things, making linear combinations. And those are the same kinds of steps that we do when we multiply matrices together. So when you want to find the inverse of a matrix, the way you do it is you take your original matrix on the left and then you build an augmented matrix on the right that is the identity matrix in the same number of dimensions as the original matrix that you wanted to invert. So you construct this thing. Then what you do is you do elementary row operations on it. You do elementary row operations until the left side now looks like an identity matrix, and the right side will have some different numbers on the right as a result of those row operations. And this thing on the right will be the inverse of the original matrix. And if you think about it, it actually kind of makes sense because you've done a bunch of multiplying and adding. You've found essentially one step at a time, one little operation at a time, the combination of all the multiplications and additions that acted on your original matrix to turn it into the identity matrix. And you tracked all of those elementary row operations by what they did to the identity matrix on the right, because you applied those operations across the whole row. And so by saying, oh, when I do this multiplication on my original matrix, it turns into the identity matrix, that means you found the inverse of it. So this is actually a pretty popular method for finding inverses of large matrices because Gaussian elimination scales in a pretty nice way as matrices get larger and larger. It's not as painful as some of the more recursive methods that I have not talked about and will not talk about because that's enough of that for the day. But it's pretty great that this works, and I'm a fan. So hope you found that interesting. I hope that all of your equations will be well behaved and that you will now solve them with greater ease than ever. With that, I will see you in class.